Let me show you how to be a good Bayesian. Change your predictions after taking information in.
As you were saying also that Bayesian stats is popular in other parts, of physics. That's definitely true in a sense that, for instance, in the car developers of PIMC, of Stan, you have a lot of physicists, often coming from statistical physics, and historically even the algorithms that we even use, CMC algorithms, have been developed mainly by physicists or for physics purposes. So there is really this intrication here, almost historically. And that made me think that if listeners are interested, there is an interesting package that's called Exoplanet. And that's a toolkit for probabilistic modeling of time series data in astronomy, but with a focus on observations of exoplanets. So that's different from what you guys do, but that's using PIMC as a backend. So that's why I know it. And that's mainly developed by Dan Furman-Mackey, if I remember correctly. I will put that in the show notes for people who are interested, because that is definitely something to check out if you are doing that kind of models. And that made me think that I didn't even thank our matchmaker, because today is February 14, but actually this episode was made possible thanks to a matchmaker, a Cupid, if you want, of Bayesian statistics, Johnny Highland. Thanks a lot for putting me in contact with Christopher and John. Johnny is a faithful listener, and I am very grateful for that and for putting me in contact with today's guests. And so you mentioned already, Christopher, that you two work on the LIGO-Virgo collaboration. Maybe, tell us a bit more about that collaboration, what that is about, and what the goal is, so that listeners have a clear background, and then we'll dive into the details.
So yes, LIGO, Virgo, Carrera is a collaboration of collaborations. So each of LIGO, Virgo, and Carrera operate their own gravitational wave detectors. So these are remarkable experimental achievements. We're talking devices that can measure distortions in space and time is what we're looking for. So in effect, what we do is we time how long it takes the laser to bounce up and down between some mirrors in one direction compared to another. We're looking for a part of less than 1 part in 10 to the 21. So it's equivalent to measuring the distance between the Earth and the Sun to the diameter of a hydrogen atom, or the distance from here to Alpha Centauri to the width of a human hair. So over many decades, experimentalists have developed the techniques to build these detectors, to design them. And we're now in a very fortunate situation that we have multiple of these detectors operating across the world. So we have 2 LIGO detectors in the US, one in Livingston, Louisiana, one in Washington, in Hanford. And we've got Virgo in Italy, just outside Pisa, Carrera underground in Japan, and in the coming decade, another LIGO to be built in India. And each of these observatories is looking for gravitational wave signals. The ideal source for gravitational waves would be a binary of 2 black holes or 2 neutron stars, very dense objects coming together, merging very quickly, very strong gravity, very dynamical objects. We can detect these gravitational waves and with those do astronomy. So instead of using a telescope to make observations with light, we're using these gravitational wave detectors to look for gravitational waves and uncover the astrophysics of these sources.
Yeah, I think so. That's a very clear explanation. It's a bit like being able to hear the universe itself only looking at it, right? So that's another way of getting information about the universe, and that maybe allows us to also answer questions that we had, but we were not able to answer only with the telescope data. Is that the case, or is that mainly information that's parallel and similar?
Yeah, I think that's one of the most exciting things about it, is it's completely separate from the electromagnetic spectrum. It's using the stretching and squeezing of space itself by these black holes and neutron stars. But the waves that are given off are kind of at audio frequency. So as you said, the detectors are picking up essentially the equivalent of sound waves, bulk motion of material rather than the jiggling of atoms. We're talking about the jiggling of whole stars and the movement of them in their orbits. And because you're looking at the bulk motion rather than the surface of the objects, you can see right into the heart of what's going on in some of these very violent events. In principle, we should be able to see also inside supernovae, if there are enough motion of material during the core collapse. That would also give off gravitational waves that we could see, although they are thought to be much weaker than those that we're looking at the moment from compact binaries.
I think one thing that's particularly nice we can do as well is really test how gravity behaves in very extreme environments. So, John, I don't know if you want to mention something about looking at the ring down of black holes.
As Christopher says, there's a very detailed prediction for how two stars should approach each other in their spiral over time. And the equations are horrendously complicated. You're talking about the full theory of general relativity. But once they've collided and they form a larger black hole, suddenly everything becomes rather simple, and it acts just like a wine glass that's been excited with a fork, and then it gradually decays down, settles into its final state. Now, for a black hole, that happens extremely fast because they want to settle down as quickly as they possibly can, if you like. So the notes that they give off are milliseconds long rather than seconds long. But the frequencies and the damping times of those notes are measurable with gravitational waves. And by looking at them and comparing them to each other, we can check to see that the predictions of the theory are indeed what we would see in the world that we can observe. So far, they do seem to be in agreement.
Yeah, and how can we even, like, something I'm wondering is that these collisions that you're talking about, they are happening millions of light years away. How are we even able to study them and also maybe tell us what we already have learned from them?
They're really quite rare events, the types of collisions that we're seeing. I mean, this is why they're millions, hundreds of millions, or even billions of light years away, is because they're so rare in the universe that we need to look out a very long way before we see one often enough to make the detections of them. So, I mean, they do happen in local galaxies as well. There's no reason to think they wouldn't, but it's just they're so rare that we haven't seen one from a nearby source yet.
They are remarkably energetic. So the amount of energy that is output as gravitational waves when you've got, say, two black holes coming together is phenomenal. For just that moment as they smash in together, more energy, so the luminosity, the amount of energy per unit time emitted right at that peak is higher in gravitational waves than if you were to add up all the visible light from all the stars that you could see in the universe. So it's a phenomenal amount of energy just over a very short way. So yeah, we just need to be listening to the universe to see these, to discover these sources and find out what they're trying to tell us.
The energy flux from these black hole collisions, despite the fact that they're hundreds of millions of light years away, is actually comparable to the flux from the full moon. So the brightest object in the night sky is surpassed by gravitational wave signals, except we can't see the gravitational waves because they don't interact very strongly with matter. And it's only by building these incredibly sensitive detectors to pick up their effect on distances that we can measure them at all.
It's fascinating to me that we're even able to hear these waves in a way. So,
I mean, just to hammer the point home, there's so much energy that they're carrying away, but the effect is so tiny, as Christopher said, 10 to the minus 21 or less. If you think about how those two things can be true at once, it's telling you that it takes an enormous amount of energy to produce a tiny distortion in space. So it's very, very difficult to warp space, and that's the consequence of general relativity.
Let me show you how to be a good Bayesian. Change your predictions after taking information in.